Okay, so a little bit of review before we continue on. From quantum mechanics, the Schrodinger equation gives us a set of solutions that can be made for that famous wave equation that electrons act as waves. And the equation with its solutions actually will solve the problem of where exactly electrons exist in these wave functions perfectly. So what we're doing and started to do is make a notation that tells me where every single electron exists based on its proximity to the nucleus in these three-dimensional standing wave functions. So in any case, a little bit of organization. The first number is the principal energy level. It's got a couple of synonyms. Okay, it's either called n equals 1 or the principal energy level. That's the 7 major shells that Bohr was talking about. You can also call it a period number. It's the first period in the periodic table, which is the same thing as a row number. Now, within this major energy level, let's make this the nucleus, okay, we have some organization. We have within the major energy level, we have a sublevel. Okay, a sublevel is within the major energy level. As we talked about Friday, in some of the leaps were not always major leaps from one to the other, as Bohr suggested. Sometimes the leaps were tiny and there was fine line structures. That's due to some energy levels within the principal energy level. So this is energy level 1. We have within it a sublevel. And that sublevel, okay, that sublevel is S for the first energy level. Okay? Okay, so within the major energy level, we have sublevels. Those sublevels can have a total of either 2 electrons if it's an S, in that S block I showed you, or 6 electrons in the P block I showed you, or the 10 electrons in the D block, or 14. And those are the only 4 sublevels that have electrons in them that we know of. Now, within the sublevel, we have orbitals. And orbitals are the places where electrons exist. Now, we draw boxes for notation. So an S would have 1 box because it has 1 orbital only, and 2 electrons exist. P, because it has 6 electrons, would have 3 orbitals. And we throw those pairs together as 3 boxes, and we would fill them as such. I'm not going to draw them, but 10 would have 5 boxes, or 5 orbitals, and F would have 7. So when we talk about the organizational electron, we want to know which energy level first. Okay, and that's why you'll see what energy level are we in, what sublevel, and then how many electrons we have in that sublevel. By knowing how many electrons we have in that sublevel, we'll know approximately how many sublevels are filled or partially filled, and we'll get to that a little bit later, definitely Monday. Okay, so that's the organization. Principal energy level, within that energy level sublevel, and then within that sublevel, appropriate number of orbitals. Okay, so let's go back to where we were. All right, so carbon, 1s2, 2s2, 2p2, okay? Or if you remembered, you'll see on the periodic table, it's going to be written as 2-4, okay? So let's go to the periodic table, different ways to look at it, and we'll see carbon, and I'll zoom in here and move it down, and you'll see that 2-4 right here, okay? So again, we're just moving across the periodic table. You should have your periodic table out as we do this. Nitrogen is the next one, so it's going to start filling that P block. So 1s2, 2s2, 2p3. Oxygen is the next one, so it's 1s2, 2s2, 2p4. Okay, fluorine is 1s2, 2s2, bless you, 2p5. Okay. And we have neon, which is the next one over, 1s2, 2s2, 2p6. And this is magical because, as I talked about before, with helium, this is the first energy level filled. Now, neon is the first element that fills its second energy level. That's not the color I wanted. Okay, second energy level. So this is 2 electrons here, and this is 8 electrons, 2-8. Now, as we talked about, okay, neon is stable. It's a noble gas. Helium's stable. What makes it stable? They have filled energy levels. Okay, helium does, and so does neon. So if you look at the periodic table, you'll see that they're at the end. Okay, so we move over, okay, we work over here. So neon and helium, they fill their energy levels. That's why the noble gases all the way to the right are always stable. They have configurations that are, of course, low energy. Okay, so back to neon, you notice it has 1s2, 2s2, 2p6, and notice we are putting every single electron in its organized place based on wave functions. Okay, that's what we're doing here. Now, more importantly, 2 electrons are filling the first energy level because we know the first energy level, like we learned, only has an s. So that makes sense. It's filled. The second energy level, as we talked about before, has an s and p. So 2 plus 6 is 8. So 8 fills the third. Okay, moving on. Now we're in the third row of the periodic table as we begin sodium. Okay, so, oops, sorry. I don't know what I just did there. Oop, I don't know what I'm doing now. Hold on. Okay, back to reality here. So we're going to go to the periodic table, and we go to the left for sodium. And notice we are in the third row. Okay, and notice the numbers, 2-8-1. So these nice little numbers are telling you that we're starting to fill the third energy level, the third principal energy level, n equals 3 that we talked about, that Bohr alluded to, but not exactly correct. So back to filling this out. Okay, so sodium, all right, again, has a total of how many electrons? 11. So we have to show every single electron. So 1s2, 2s2, 2p6, okay, and of course we have now 3s1. All right, so if we look at our configurations, which is written, let's go a little thicker here. Okay, 1s2, so that's 2 plus 2 plus 6 plus 1, and that gives me a total of 11 electrons. And again, if you were to do the dashes, 2 dash 8 dash 1, 8 in the second, which is now filled. Okay, now as we talked about before, in the case of sodium, sodium has some valence electrons. This S2 is filled. Now the second energy is level filled. And look at this. The electrons that we're talking about here that are outside the outermost electrons are valence. Notice sodium has one valence electron. It's one electron outside the filled, just like lithium. Wow, they have the same valence. Notice lithium and sodium are in the same row. They have the same valence electrons. So magnesium is 1 over, 1s2, 2s2, 2p6, and then 3s2. Notice it has how many valence electrons? 2 that are outside the filled principal energy levels. These are kernel electrons, we call them. Okay, they're filled. These are called valence electrons. These are available for bonding. These are not. These are stable, low energy. Notice beryllium and magnesium have the same valence electrons, and if you go to the periodic table, okay, you'll see they're under each other. Beryllium, magnesium, and you notice they all become +2. Whoa, why do they all become +2? Because beryllium, okay, can become stable just like magnesium by losing those 2 electrons. Now beryllium loses 2 electrons to become like helium. Magnesium will lose 2 electrons to become like neon. Okay, neon, if you remember down on the bottom, is this configuration. So the driving force between charges, or why things lose or gain electrons, is to become stable. Magnesium, look right here, loses 2 to become 2-8. 2-8, okay, is across the periodic table, all right, is right there, neon. And look at helium, just 2, which is really, you know, that's 1s2. They give you the easy ones. And lithium loses 1 to become 2, or 1s2. Beryllium loses 2, so the driving force, look at these guys. Lithium, Na, sodium, K, potassium, they all become +1 because they all lose that 1 outer electron. These guys, guess what? Lose 2 electrons because it's easier to lose 2 to become 2-8 or than to gain 6. On the other side of the coin, fluorine, 2-7, needs 1 more to be stable. That's why it is -1. So we're explaining through electron configurations now for the first time why these elements actually gain these 2. Look at oxygen. It gains 2 to become 2-8. Now we know this is really 1s2, 2s2, 2p4, So it needs 2 more electrons to fill its 6, for 2p6 to be like neon. So now, aha, we have the driving force behind why things gain electrons or why things lose. Okay? All right, and of course chemical properties. Now aluminum is 1 over, so now we're just going to keep flying around here. So 1s2, 2s2, 2p6, okay, now 3s2, 3p1. Okay, silicon's 1 over, so you get the idea. 1s2, 2s2, 2p6, 3s2, 3p2. All right, oops, where am I going? Oops. Okay, and now I have phosphorus 1 over, 1s2, 2s2, 2p6, 3s2, 3p3. And the beat goes on. Hold on. So once you go ahead and fill out sulfur, chlorine, and argon, I'll be right back with you. Just pausing so that you pause. Pause, 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 pause the button, and I'll do sulfur, chlorine, and argon. Pretty simple stuff, just going right in order. Okay, so sulfur, 1s2, 2s2, 2p6, 3s2, 3p4. We're filling that p block as we go from sulfur to chlorine to argon. And you notice argon is again an example of a very stable configuration, but as not quite like neon. If you notice, neon had a stable first energy level that's filled and a second that's filled. And you may guess, well, the third is filled, but remember that the third sublevel has an S, a P, S, and a D. Third energy level has 3 sublevels. The fourth energy level has an F added to the 3. So the energy level here equals the number of sublevels. So it's still stable, but by a different set of rules, okay? Remember, filling energy levels is stable, okay, if in fact we fill that energy level very, very stable. But we also can be very stable here too, because if you remember, the energy levels like Bohr were exact with no sublevels. Okay, undo. And now that we have sublevels, there actually is some stability within finishing. There's something about filling the S and P of one sublevel. So although argon truthfully does not have a completely filled third, you fill the P sublevel with the S in the same energy level, there's something about the stability here. So we say argon has no valence electrons. Upstairs. You want to go upstairs? Okay, hold on. So although argon does not have a filled third principal energy level, we consider these electrons here to be very, very stable, just as stable as this. So argon has a very, very stable configuration and does not react. Okay, but you should know the real deal here is that it doesn't truthfully have a third filled energy level, but stable because it fills the S and the P nonetheless. We consider argon to have no electrons available for bonding, just like neon. Chlorine, okay, has how many valence electrons? Now, I know some people would say, well, it has 5, but that's not right. It has 7 valence electrons, just like fluorine has 7 valence electrons. These guys are in the same column because they have the same chemical properties, because they all just need 1 electron to become stable like their noble gas counterpart. So they want to be just as stable, so they'll gain 1. So my friends, in chemistry, I can't say enough, the valence electron here is 7. These, you have to add the 5 plus the 2. When you look at the reference table for chlorine and fluorine, okay, we'll see that their valence electrons can be identified. Oops, let me go over there. I have a tough time moving this over. It's like backwards. Then I think sometimes. Okay, so getting over here. Okay, look at fluorine and chlorine. Okay, they 2-7, 2-8-7. That 7 is valence electrons. Now, one quick way to get valence electrons is you can take this number 1 away, and there are 7 valence electrons for all of these in the same column. That's why they have similar chemical properties, because they have similar amount of electrons that are unstable. Take the 1 away from here, and you got 6 valence electrons. Look at that, 2-6, 2-8-6. All of these guys in the same column, same chemical properties, same availability of electrons for bonding. So this 6 valence electrons are from 2 from the S, 2s2, and 4 from the P, 2p4 together, and so on. And the beat goes on. Now the ones over here, these guys all have 1 valence electron, the number 1. They don't have a number in front, so there's the 1. This has 2. And the middle have a different scenario we'll get to. So yeah, over here you can just take the 1 away, except for these guys here. Even though there's take the 1 away, these typically have no valence because they have no availability of electrons for bonding. We know neon and helium and neon have 2 filled. This has 1 filled, completely filled Prince Modular level, very stable. Neon has exactly 2. Argon does not have 3, but is very stable. Okay, and you notice krypton doesn't have 4, but is completely stable. And you should know 2, 8, 18, 32 fills the 4th. But there's something about filling that P. This is 2p5 row, 2p6 row. All right, so again, let's go back to where we were. All right, so moving back on, potassium, we're starting the 4th row. So I'm getting an opportunity now to fill in potassium to calcium now. We're going to pause it and do potassium. Okay, so potassium has the same configuration as our neon gas, as argon below, 1s2, 2s2, 2p6, 3s2, 3p6, and the only additional thing we have now is the 4s1. One more. Notice we're starting in the 4s block again. Calcium is 4s2. Okay. All right, little mistake there. But the bottom line is we're showing all the electrons. If you count these exponents, they equal to the total number of electrons. And of course, this has 1 valence electron, just like sodium, just like lithium. They're in the same group. Same group means they have similar chemical properties. And the configurations show that. Same thing here, 2 valence electrons. Okay, easy enough. Now, scandium and titanium, let's look at the periodic table and pause this for a second. Now, I want you to look very carefully. This other type of configuration that's easy is showing electrons in each energy level. 2 electrons in the first, 8, okay, in the second, 8, and the third. And now we have 1 more adding to the 4th. But we learned that there are 3 sublevels for the 3rd energy level, an S, a P, and a D, and that should add up to 18. Yet we're filling the 4th energy level before we fill the 3rd. And that's because of a little bit of overlapping between the 4th energy level, between the 3rd energy level and the 4th. The 4s starts filling, okay, before this fills. Now scandium, you notice calcium is 2-8-8-2. Okay, this is the 4s2 that 2 represents. Now look at this number, 2-8-9-2. This 9 we're adding to the 3rd energy level. And that means that this must be 3D1. 4s1, 4s2, 3D. Mr. Grodsky, this is not in the 3rd row. You're right. The 3D starts in this block here because the 4s orbital of the 4th energy level starts before the 3rd finishes. And this is proven. Look at 2-8-9-2, 2-8-10. We're adding electrons to the 3rd energy level as we fill the D. And if you remember, when I showed you in the first lecture of this series this weekend, and I'm kind of probably going to have to pause to show you. Oops, let me do that. Okay, I'm back. Remember when I showed you, this is the D block. Notice it's 4s1, 4s2. There's our the 2 elements we just did. And then we have scandium right here. Look at that. That's the 3D. Why isn't the 3D in the 3rd row? That's the biggest question we have at this point. It's because the 4s fills first. The 4s actually starts before the 3D. So you have 3D1, so 4s2, 3D1, 3D2, 3D3, 3. And once we fill the Ds, we're back to the 4Ps. So the S and the P of the same energy level always match the row number or the period number. But the D is 1 behind. Now, I'm probably not going to get to this. The F, where do you think the F starts? Okay, well, if you look in your periodic table, there's going to be a detour in here. Okay, the F actually starts right in here, and I don't know if I have that in the other drawing. Yeah, I do, but it didn't show very well. Okay, so the other one shows it. The F starts right in here. So let's go back to where we were. Okay, so scandium, okay, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2 for the calcium, but now 3d1. The 4s starts before the 3d finishes. What we have is overlapping. Here's the D, okay, and here is, let's say, the 4 starting before the 3D finishes. From this point on, there's a lot of overlapping, okay, and it kind of makes sense. These things are waves, so waves have a tendency to overlap on each other, as we've talked about, constructive and deconstructively, okay. So I'd like you to fill this out, okay, on your own. And I want you to use the Flash animator to help you with that. And I'll talk about why there's some weird changes in here. I don't think you'll be able to do the silver and uranium, but you can try that with the Flash animator. I want to show you that for a second. Okay, so I'm in the in our website right now, and I'm showing you what I've embedded. Hopefully you can see this. And notice if I click on hydrogen, okay, maybe it's 1s1. Okay, helium, 1s2. And notice I'm filling these electrons in these boxes. These boxes are orbitals. We know that they're shapes. Now let's go on to calcium. Okay, like we just did. We have potassium, calcium. Now we're going to go to scandium. So we're filled 1s2, 2s2. Notice they did something here. They used argon as a shorthand notation. Argon is 1s2, 2s2, 2p6, 3s2, 3p6, and this is entirely argon, a shorthand way to say, okay, all of argon plus 4s2. Okay, right now I want you to use the longhand method to get there. Now, the 4s2 fills before the 3d. So what happens? Scandium, 3d1. Titanium, 3d2. Vanadium, 3d3. Chromium, so you can build it that way. Now, there's some things happening here I'm going to explain to you on Monday. It's called the Hud's rule. It's in your notes. Okay. All right. So we're done here. Finish it out the best way you can. The one below it can do the higher ones. Okay. The uranium or whatever I was asking, silver. You can try that. And notice this F group actually sneaks in here right after barium. Okay. The other one. So here's barium. Okay. And then the lanthanide series. Ooh. Now we're starting to fill that. There's a D1, and then that comes next for the F. I'll talk about all that, some more overlapping. Okay? Thank you for participating. It really is helpful.